It gives me great pleasure this morning to introduce the Professor Hideo Hosono from Tokyo Technology University. He is a pioneer in the Oxide Semiconductor. Because of his work, we have some of the most beautiful televisions that also because OLED work as well in the market today. Professor Hosono got his PhD in 1982, I believe, from the Tokyo Metropolitan University. And after PhD, he became the assistant professor at Nagoya Universities. And let me see it. In 1993, he moved on to back to Tokyo to become a professor at the Tokyo Technology Universities. And in beginning 2012, he was the director of the Material Research Center for Adamant Strategies. And today he's going to give a talk on organic semiconductor for flat panel displays. Professor Hosono has received a lot of awards. The prestigious one from his own country is the Japan Prize in 2016. Let me give you the citations for that prize. So creations of unconventional inorganic materials with novel electronic functions based on nanostructure engineering. Without much ado.
Okay, thank you very much for kind introduction. Yeah, so my name is Hideo Hosono of Tokyo Tech. So today I would like to talk about our research on oxide semiconductor for flat panel display. As this picture was taken when last year the president of the LG Display visited our lab and donated 65 inches OLED TV. So that I started the oxide and semiconductor work from 1993. So at that time, I totally could not imagine such a thing happens. Okay, so this is a building of our research center. So the construction structure of this building is quite interesting. That is to say, this is a periodic table. How many elements in one row? How many elements? 18, okay? Number of the windows is also, So which element do you like? I liked the hydrogen, always hydrogen. My room is here. Okay, this is the outline of the talk. First, I will show you that the outline of the oxide semiconductors. The semiconductor of the oxide is essentially different from the silicon. So as the next is, this is almost the history of the oxide semiconductors, material design of the transparent amorphous oxide semiconductors. And this is a little bit current issues as transparent amorphous oxide semiconductor and NBIS and instability issues. And P-channel, but maybe not so time to introduce this one. And last one is new material for OLED driven by oxide TFT. This is, we are now focused on this subject. Okay, so the history of the oxide TFT, oxide material semiconductor is very old. So the indium oxide, zinc oxide, and tin oxide already started in 1960. So we started in the early 1990s and created the series of the material. This is a crystal, and this is amorphous. Okay, this is amorphous, and This is N-type. Oxide semiconductor is mostly N-type. P-type is very difficult. Okay, so that P-type material, only Cu2O was known in 1960s. And nickel oxide, but nickel oxide mobility is very small. So in 1997, we created the transparent as P-type semiconductor. By using a copper aluminum oxide. After that, so we fabricated that amorphous as a PN junction. But the mobility of these material, amorphous P-type material, not so large. But anyway, and so our material research target was to realize as bipolar oxide as TFT. We realized as these devices by using SNO. Okay, so how do the oxide differ from the silicon? Okay, so silicon is of course a covalent bonding, and so that as valence band and conduction band are both composed of the silicon sp3. The crystal structure is very simple. Always diamond type. And on the other hand, it's oxide. Is ionic. So the ionic means that the nature of the valence band is totally different from that of the conduction band. So the electron pathway is primarily composed of the vacant orbital of the metals. Okay, so but the valence band top whole transport layer is always oxygen 2p. No unique, no varieties. So the oxygen is negative, so that when the hole is doped, so the resulting hole tend to localize at the valence band top. This is the reason why P-type oxide semiconductor is very difficult. On the other hand, it's N-type. So N-type is how to choose the element to have a large mobility for large mobility. So there are so many options of the candidate of the cation, so that the N-type is not so difficult. Okay, so that but the crystal structure is also so many variety. So that we focus on such a two-dimensional material or the one-dimensional material. But anyway, it's. I focus on an amorphous semiconductor here. Okay, so that you know that ITO. Okay, why ITO work as transparent conductors? Why? How the ITO is unique? Okay, so that designing N-type transparent conductive oxide. This is very simple. Okay, so that this is a tin oxide. So that 5s orbital, vacant 5s orbital is radius. So the overlap between neighboring 5s orbital is very easy because it's and overlap between neighboring 5s orbital is large because it's connection of the octahedral is shared by edge, so that interatomic distance becomes shorter. Okay, that's why large, especially large spread s orbital and at a short interatomic distance, both are needed to realize the large electron mobility, spatially spread vacant s orbital and shorter interatomic distance. So but please remember the titanium dioxide. Titanium dioxide is 3D. So the d orbital is not so spatially spread. So that's why mobility of the TiO2 is not so large. So the TCO trigonal, TCO is easily obtained by combination of these 5 elements. Okay? This is example of the ITO. Metal indium is, of course, invisible. Light is reflected. indium oxide. It's stoichiometric indium oxide is an insulator that it's light and easily pass through the material. Okay, but when this is a near space structure, so that the indium is indium and this is oxygen. Indium is not connected. But if we draw the indium 5s orbital, okay, it's drawn on the crystal structure, you can see the direct overlap between indium 5s orbital. Okay, so the near space ionic radius is not. This is the aerospace structure. Indium is not connected, but at the bottom of the conduction band, indium 5s orbital is easily overlap. Okay, so this means that when the electron is doped, electron easily become mobile. So the already highway for electron is established at the bottom of the conduction band. Okay, don't focus on the real structure. The orbital structure is essential. Okay, so that's our focus is amorphous oxide semiconductor. Okay, this is a typical semiconductor, covalent type semiconductor like a silicon. We focus on N-type. P-type is a different story. So that the bottom of the conduction band of the silicon is like this, the sp3 hybridized orbital from its three-dimensional network. Of course, the sp3 is highly anisotropic, and so that there's no bond around here. But in the crystal, overlap between sp3 orbital is optimized. That's why mobility is so high. When such a crystal become amorphous, what happens? So the mobility is drastically dropped to 1. So that this is due to the not optimized overlap between highly anisotropic sp3 orbital. Okay, so this means that the amorphous silicon is very easy to fabricate homogeneous thin film that the electron transport become so bad. Okay, this is also true for gallium arsenide or the gallium nitride. Okay, so that amorphous semiconductor is very easy to fabricate. So at low temperature, but electron transport is pretty bad. This is almost accepted image of the amorphous semiconductors. But I don't believe this is not always true. Okay? Oh, sorry. Okay, so please consider the heavy metal oxide. Okay? It's a heavy metal oxide like an indium oxide, so that at the bottom of the conduction band, it's a large spread s orbital is connected each other. Contribution of the oxygen to P is very small. And it's heavy metal cations has a large spread s orbital, so that the s orbital is directly connected like this. So that this is like a string composed of the metal ball. So the stretched state corresponding to the crystal, while that folded state corresponding to the amorphous. Okay, so that if such a state is realized, so the conductivity doesn't change so much. This is my guess. So that okay, so that I presented this idea and in amorphous semiconductor conference, which was held at Kobe. At the time, big earthquake happens. Almost more than 20 years ago. Okay, so at the time, amorphous silicon was the strongest. So the total number of the presentation were maybe 700. Oxide paper is only one. This paper. Okay, so that so that I presented this paper. So that's but almost no response. So that some expert says that Hosono-san, this is not your place. This is not a glass conference, but a semiconductor conference. This is a real story. So okay, so that but it's wrote proceedings paper. And so this paper was published in the next year, so that I marked as candidate element for this material, novel oxide amorphous semiconductor with large electron mobilities. Okay, so the number of the citation of this paper was only 4 until 2003. The 2 out of 4 was my self-citation. Yeah, this is real story. Real story. Okay, but we continue the research. So the first step we did was to demonstrate the basic idea that I presented. Okay, so this is one of the examples of our material, cadmium germanate. Okay, cadmium will satisfy my working hypothesis 5s0. Okay, so as deposited thin film is transparent and insulating. But when a proton is implanted, conductivity is easily changed from here to here. And the activation energy is changed from 1 AB to less than 1 AB, 1 milli AB. So this means that the Fermi level is controllable from the mid state of the gap to the conduction band minimum. Okay, so that's I realized that and even amorphous semiconductor Fermi level is can be continuously controllable, and also the mobility of the amorphous is 15. Okay, polycrystalline sample has 20, so it doesn't change so much. Okay, so how to demonstrate the working hypothesis was not so easy. So that we constructed the inverse photoemission spectrometer. Okay, and this is the observed density of state of the amorphous cadmium germanate. Okay, this is occupied state probed by UPS. So that the problem is we need to dose of the unoccupied state. This is a dose probed by inverse photoemission. So that the Fermi level is located here. That this position located to the tail of the unoccupied state. This means that this is N-type semiconductor. And we determine the atomic position and calculate the density of state. Okay, this is calculated density of state. Okay, so that we focus on the bottom of the conduction band. It's cadmium and 5s predominantly occupies this state. This is just we expected. Okay, so so this picture shows that the connectivity of the cadmium 5s orbital at the bottom of the conduction band. Okay, so that's when the cadmium and distance is smaller than double of the cadmium 5s orbital. Okay, at the time we connected the two cadmium by straight line. Okay, this means that cadmium 5s orbital is overlap is very large. Okay, so that you can see from here to here. So the percolation path is easily observed at the bottom of the conduction band. This means that even the amorphous state is conduction path is formed by cadmium 5s orbital like a crystal. Okay, so that the fundamental science was now established, so that we moved to the TFT fabrication. This is the principle of the active matrix LCD already is almost the same. Anyway, it's TFT work as a switch of the circuit. And its LCD cases, it's most of the time is off state. Off state means that, its duty ratio is 0.1%. Then most of the time is off state. So that to save the energy, how to reduce current is key. Off state to keep a low current state is very important to realize low energy consumption. Okay, this is the history of the oxide TFT. Someone says that the oxide TFT is a new subject, totally wrong. Very, very old. 1960s, so there's so many, already, and such a representative oxide TFT were studied. So that from the here to here, almost so no paper in the public domain. At the time, I heard Judge Kaneki, when he was in IBM, IBM spent much time to fabricate the zinc oxide TFT. But the zinc oxide TFT is unstable. So the large hysteresis was almost impossible to suppress. So that when he visited my lab, he said, what are you doing? It's oxide TFT. Stop. So the zinc oxide, the IBM spent 20 years for zinc oxide TFT. So that, hysteresis was impossible to avoid. So I said that's amorphous. So he very surprised. Zinc oxide cannot form amorphous. Okay? But anyway, research was done in a company. So then from the 2000, so many oxide TFT, polycrystalline TFT started again, revisit. So we focus on 1995 is a proposal of the TAOS, and it's this is polycrystalline TFT. There are so many, and the solution process it's TFT. Okay, so among the various kind of oxide, we focus on this material, indium gallium zinc oxide. Okay, this is quite interesting material. Okay, so N equal 1 to 200. So such a material is easily obtained. That is to say, so that this is indium gallium O3 and zinc oxide M. Okay, so that zinc oxide doped with gallium is a representative TCO because it's 3 plus gallium substituted the zinc 2 plus side. It's producing 1 electron. Okay, but gallium 3 plus in this material doesn't substitute the zinc side. Okay, so that gallium occupies the bottom triangle, or central part of the bottom of the zinc oxide, it's a tetrahedron. And it's a tetrahedra, it's reversely connected. So that gallium does not substitute the zinc side. So that, this is very good. And so that maybe that we can suppress carrier concentration if we obtain the high quality epitaxial simple. And we try to fabricate the epitaxial symphony of this material. Okay? So that, we developed it's quite interesting, very easy process called reactive epitaxial, solid-state epitaxy. Just deposit on the epitaxial thin film a very thin layer of the zinc oxide and deposit the amorphous thin film, and it's capped by YSZ and heated up That's all. So following this procedure, we can obtain such a beautiful epitaxial thin film. Okay, so this is the case of the N equal 4. So the four layer of the zinc oxide, and this is indium gallium layers. Okay, so that from here to here, epitaxial growth is obtained. So as expected, so that this material is semiconducting. So the carrier concentration is below 10 to the 14. Okay, but the polycrystalline IGZO thin film was studied as a candidate of the ITO alternative, TCO. Okay, how to enhance carrier concentration was people concentrated. So our research is totally different. So the intrinsic nature of this material should be a semiconductor. So we obtained semiconducting low carrier concentration of the IGZO and fabricates the TFT. So the TFT mobility is 80. Yeah, very surprised. That's at the time. This mobility is comparable to the polycrystalline silicon, so that we realize that this material has a huge potential as an active channel of the TFT. So that of course, we skip the polycrystal because the polycrystal has a lot of the issues as like a zinc oxide. So we fabricate on amorphous and indium gallium zinc oxide. Okay. Now, so the amorphous is easily obtained very wide region, except this region and this region. And mobility, this is whole effect mobility. Mobility is just increasing, is increasing the indium oxide. And the highest mobility is obtained around here. So the 20% is the zinc oxide and 80% of the indium gallium indium oxide. So that this just corresponding to the IZO, which was used as an amorphous TCO by Idemitsu. Okay? So that still this chemical composition is the largest in the whole mobility. Okay? But we first fabricate the TFT for this chemical composition so that stability is pretty bad. When a sample was deposited in the oxygen-rich atmosphere, obtained the TFT shows the highest mobility. But when the sample was placed in ambient atmosphere, so the off state is going up. So pretty bad in stability. So that we abandoned to use this chemical composition. So we focus on stable chemical composition. That is to say, 111. 111 is so the mobility of the 10 is easily obtained. When the chemical composition is deviated, plus minus 5%, no problem. So the important thing is a lot of gallium. So TCO is a metal. So how to reduce carrier concentration without degrading whole mobility. That is the essence for application to TFT. Okay? So the gallium is very important. So because the gallium occupies a 5-fold coordination. Okay? So that when we publish a paper on amorphous IGZO TFT, so the amorphous silicon guy asked me so much, why your oxide TFT shows the high mobilities? Amorphous silicon's case is always, and its mobility is below 1. So, and band conduction doesn't occur. So this is a famous paper by Walter Spear and it's Lucomber, amorphous silicon, 1975. Okay, when phosphorus is doped, conductivity goes up. Okay, but still Fermi level is located. It's stopped here. It's 0.2 EV. It's below the conduction band bottom. When the hole is doped, yeah, conductivity is also going up, but still remain a gap. Band conduction doesn't occur. Okay, so that's why the amorphous silicon's mobility is very low. When mobility film level exceeds exceeds the mobility gap, so mobility should be a 10, about 10. But the observed one is always 0.5. So that this phenomena is reasonably explained by the so-called the Bob-Street model. So that is to say, when phosphorus is doped, the silicon substitution occurs, but the resulting electron lead to the dissociation of the silicon bond. So as a consequence, and the silicon 3-fold coordination with one lone pair is formed. So the electron, carrier electron doesn't occur. Okay, so that this is very, very reasonable model. But what is this? This is covalent bonding. Covalent bonding. So that the lone pair, the concept of the lone pair doesn't work for the ionic compound. So that's why we don't. Oxide semiconductor doesn't follow the Bob-Street model. Okay, such a local covalent bonding is not obtained in ionic oxide semiconductors. Okay, this is electron transport property of the amorphous IgGO. Okay, this is carrier concentration. This is hole mobility. Okay. So in amorphous semiconductor, hole mobility cannot be measured. This is almost a common sense, okay, so far. So the hole effect gives a negative sign, or the reverse sign of the true real carrier. So that the amorphous silicon case, when the phosphorus is doped, and polarity obtained by hole effect become plus. Always reverse. So this is hole effect anomaly, sign anomaly. But the oxide TFT, so that the hole mobility is reliable. Well, because the mean free path of the oxide TFT is so long. That is the reason that so the local mean free path is one order higher than the shortest chemical bonding, so that the hole effect mobility is reliable. So that this is hole mobility and carrier concentration. When the carrier concentration is low, and the mobility is also low. Okay, and after that, it's increased. So this is totally different from the case of the crystalline silicon. Crystalline silicon is when carrier impurity is doped, mobility is rapidly going down due to the impurity scattering. Okay, this is totally different. And also this is temperature dependence of the hole mobilities. Okay, so when the carrier concentration is low, thermal activated type, and after that, activation energy becomes low and eventually become flat. This is almost a crystalline semiconductors. Okay, so when I obtained this sample, very surprising. Okay, so when carrier concentration higher than 2 times 10 to the 18th, film level enters the bottom of the conduction band. So the degenerate conduction occurred even in amorphous state. Okay? So the amorphous silicon was amorphous chalcogenide. Such a state is not realized. Only oxide can do. Why such a thing happens? Okay? Very, very simple. At the bottom of the conduction band, of course, potential fluctuation exists as reflecting the structural randomness. Okay? But covalent semiconductor like silicon or chalcogenide, so the potential fluctuation is very deep, okay, because bond is very, very directional, okay? But the ionic bonding is potential is just R over 1 over R, Okay, very is not so sharp, and so that when the carrier is doped, like here, so that such a shallow valley is easily filled by 2 times 10 to the 18th. After that, almost like a crystal. Okay. Okay. So the IGGO case have 3 cations: indium, gallium, and zinc. So what is the most critical to control the carrier mobilities? Of course, indium. So that we calculated the metal orbital at the bottom of the conduction band. So you can see that the 3-dimensional calculation of the indium 5s is observed. So that the electron mobility is controlled by indium concentration. Okay, so the role of the gallium is to suppress the carrier generation. Zinc is not so essential. This is our conclusion for amorphous IGGO. Okay, so that maybe this paper is well known. So that the TFT mobility of the 111 IGZO is 14. Okay, so that we calculated the density of state and mid-gap state. This is amorphous silicon cases. This is a Fermi level located here. This is a conduction band bottom. So to induce the band conduction, we push up the Fermi level from here to here. Okay, but at the bottom of the conduction band, 10 to the 20s. 21, very huge tail state must be overcome. But on the other hand, in the IGZO cases, this is a conduction band bottom. Fermi level is located here, so that 3 order less as the tail state density. That's why we can easily obtain the band conduction. Okay, this is the picture of the polycrystalline and indium gallium zinc oxide target for sputtering. Yeah, it's 3 meter by 3.5 meters. This is Gen 8 size substrate. Now the Gen 11 factory is constructing, so that much bigger. He was a president of the ARVAC, so they produce it's a large size IGGO target at that time. Okay, so this is the history of the research and the product. So that and so real application of the IGZO started from the 2012, and it's a smartphone and it's iMac, and this is iPad mini maybe, and 55 inches OLED, and Microsoft Surface Pro 4, which I'm now using for presentation. And it's 55 inches and 65 inches OLED. Okay, this is the general feature of the Oxide TFT. So it's the mobility, it's maybe the maximum mobility for the stable operation is maybe 30. So 50 is not so easy. So that's and it's no inversion and operation, always N-type. Okay, so that band PN inversion doesn't occur. This is work favorable to reduce energy consumption. This is totally different from the silicon LTPS. LTPS is bipolar, so that when the gate voltage is reversed, so that P channel operate, so that the energy consumption is not so small for the LTPS. and also optical transparent. And so this is very important. So the oxide TFT performance and stability is pretty sensitive to the post-annealing and its partial oxygen pressures. And that's one of the material characteristics of the oxide. Oxide is only one material, a semiconductor, which can be heated in air. Oxide can heat even in air. So this is totally different from the silicon or organics. This is the reason that as so many people are doing on a solution process, oxide TFT. Okay, so the P channel is our target. So P channel is not so easy. So P-type zinc oxide, so many papers were published, but I don't believe that any paper. No, yeah. So that, this is zinc oxide. And zinc, not SNO. SNO2 is N-type. This is SNO. Okay? So because it's, SN2 plus has a 5s2 electronic configuration. Okay? So that 5s occupied state occupies at the top of the valence band of this material. Okay? So that almost a reverse situation of the N-type material. Okay? So that when the hole is doped, so that spatially spread, occupied S-state overlap each other, so that this material work as a P channel. So as expected, so that we obtained the P channel oxide TFT. Mobility is not so good, but anyway, the P channel as work for the first time for SNO. Okay, this is recent data. Okay, yeah. So I abandoned to realize a high mobility, transparent P-type semiconductor. Oxide is not so good. This is my guess. Oxide is negative. Okay, so more we have to change the idea so that we focus on iodide, almost close to the perovskite. Okay, so iodide is of course at 5s electronic configuration. No, I minus is a 5p6. Okay, so there are 3 p orbital, occupies 3 orbital. Okay, spatial spreading of the 5p orbital is very huge, 200 picometer. So this is larger than the Indian 5s orbital. Okay, 3p orbital is occupied. So look from the outside, almost occupied S state. Okay, so that when CUI become amorphous, okay, so that this material should work as a P-type semiconductors. Okay, this is my previous design of the oxide N-type semiconductor. Okay, like here, so that this is S orbital, unoccupied S orbital of the metal. Okay, the amorphous, and so we regarded the 5 occupied p orbital of the iodine is regarded as occupied pseudo S orbital. Okay, almost the same situation. So, the CUI is well known as the crystalline semiconductor, P-type semiconductor, completely transparent, but as amorphous cannot be formed. So that we modify this material, and the CUI dissolved in organic solvent and added in an SN-I4 and dropped in the solution process. And obtained just drying the sample, so that we obtained this thin film. So mobility is 8. Okay, just drying. We very surprised that So the past 20 years, our group have concentrated on oxide P-type semiconductor. Maximum mobility was 1. This case is just by fabricated by spin coating, we obtained almost 10. So this value is almost comparable to the polycrystalline thin film. And also this material is quite interesting. So that's, this is ionization potential, this is electron affinity. So that this material is pretty close to the organic perovskite or the CPB. So that this material can be applied as a whole transport layer of the organic or the perovskite and whole injection layer. Okay, from here, as we focus on instability issues, this is current status, current understanding of the amorphous IgGO. Okay, so this is conduction band bottom, this is the valence band top, so the Fermi level is located here. Okay, so fortunately, so that around the Fermi level, there's not so large defect density. Okay, but there is very huge density of state above valence band top. Well, yeah, so we detected such a dose by hard X-ray photoemission spectroscopy. Okay, so that to operate the N channel, we need to upshift the Fermi level from here to here, so not so big of obstruction. That's why we can easily induce band conduction. But when negative voltage is applied, so that the Fermi level is going down, and stopped here due to the presence of the large dose. Okay, this is the reason why P channel doesn't open for oxide TFT. Okay, this is very good to suppress energy consumption in the off state, but the presence of such a large dose causes the instability issue, so-called NBIS. Okay, so NBIS is the remaining issue of the oxide TFT. That is to say, so the normal operation is like this, but and when negative gate bias was applied under illumination, this is operation condition. So the threshold voltage is shifted to become negative. Okay, and so for the LCD has application, so the not so serious, but OLED application, OLED is current-driven devices, so that the such a large shift of the threshold is very critical. Okay, so this is the first data, so we presented in SID at the 2008, so that with George Kanicki, so that this is light sensitivity. So the below and above 460 nanometer device is stable, but when light shorter than 460 nanometer, off state is increased. Okay, so the band gap, optical band gap of the IgGO is 380 nanometer. Okay, so that this means that subgap state should be there. Okay, so that this is a negative bias stress instability. So this is almost a common test by using white lead. It's maximum maybe 440 or 450 nanometer light, and it's shined at backlight, and at the time threshold voltage is shifted. What happens? Okay, and intrinsic band gap is 3 eB, but 2.4 eB is the threshold, so that something happens. Okay, so that NBIS instability is universal in oxide TFT, not the IgGO. So the first data was obtained for the polycrystalline zinc oxide, and it's zinc tin oxide. So the various kind of so all kind of the oxide TFT suffer from such instabilities. What is the origin? Okay, so we need to identify the density of state above the valence band top. So we utilize a hard X-ray photoemission spectroscopy. Hard X-ray is 6 K or the 8 K. Okay, so that's why the hard X-ray is so important. So the conventional UPS escape depth of the photoelectron is just 2 to 3 angstrom from the surface, top surface. Okay, so there's such a it's a thin layer is easily contaminated. So the obtained data is not reliable. So at first we abandoned to extract the surface dose from the TFT by using photo emission. But hard X-ray is totally different. So the escape depth of the photoelectron is 2 to 3 nanometer from the top surface. So this is bulk sensitive. And also, ionization cross-section of the S electron is large. The conventional lab XUPS or the XPS has almost no sensitivity to the S state. Okay, so defect electron trapped in the S electron in oxygen vacancy should be a S state, so that such a electron cannot be easily detected by conventional UPS. So that's why we apply the hard X-ray photo emission. So this is data. Okay, this is a formula. This is the valence band top. You can see the large dose around here. Its minimum is at the time, so the 2 times the 20. Maximum is almost 10 to the 21st. Very huge. We're very surprised. So that there is a extra subgap state in the gap state. So that which side was the bottom of the valence band and bottom of the conduction band was the top of the valence band. This data shows that the top of the valence band has a subgap state. Okay, this is very, very clear. So what is the origin of this gap state? Okay, this is the mechanism proposed of the NBIS. That is to say, and subgap state above valence band top is excited. Okay, photo-excited, and its electron is excited to the conduction band bottom, but the electron mobility is large, so they easily diffuse away. The remaining hole or proton is drifted by negative bias and accumulated at the interface of the gate insulator and the semiconductor. So as a consequence, so the threshold voltage is shifted negative. This is the mechanism of the NBIS instabilities. The problem is what is the origin of this state? Okay, there are several models. The one is, of course, an oxygen vacancy model. It's very straightforward. Oh, sorry, this is not oxygen vacancy model. Another is hydroxyl group, or the excess oxygen is also proposed, but no direct evidence to support the origin of the subgap state. So we notice that amorphous IgG thin film for the TFT contain a lot of hydrogen, 10 to the 20s. Really practically applied for TFT containing such a large amount of the hydrogen. Okay, 10 to the 20s. Okay, so we saw that this data shows that density of that hydrogen is 10 to the 20. This is almost the same order of the subgap state above valence band top. so that the hydrogen would be closely related to the origin of the subgap state. Okay, but the hydrogen has a very, very unique element. That is to say, so most of the people believe that, hydrogen is proton, of course, at the H node or the H minus. Okay, H minus is totally different from the H plus. The ionic size is almost zero. This case is almost pretty close to the oxygen. Okay, so the H minus ionic radius is close to that of the O double minus. Okay, so we approach the origin of the subgap state by simulation and experiment. So we deposit the amorphous in IgGO, and it's measure the infrared absorption and transmission absorption spectra. Okay, so this is absorption spectrum. Okay, so that when we enlarge this portion, we can see that the three band structure. Okay, and this is OH. Broad band is hydrogen bonded OH. This is already we know. So that what is these three band? So this is oxygen vacancy model generated by molecular dynamics. So when I take out, such a local structure containing oxygen vacancy is taken out and inputs a hydrogen molecule, what happens by simulation? Okay, so that this is neutral oxygen vacancy. Oxygen vacancy occupies two electrons. So two electrons react with a hydrogen molecule to form such a state. Okay, such a state, vibrational spectroscopy frequency is calculated by using such a local structure. So this corresponding to a metal hydrogen bond. So each metal hydrogen bond gives almost an observed frequency. Okay, this means that metal hydrogen bond is obtained and is included in amorphous structures. So and also another important information is oxygen vacancy is unstable. When the hydrogen is included, so they easily react with hydrogen to form a metal hydrogen bond. Okay. Okay, and thermal behavior of the incorporated the metal hydrogen bond is totally different from so-called OH. That is to say, okay, this is thermal stability. This is a metal hydrogen bond, H minus. So this is on OH bonding and incorporated in amorphous structures. When the sample is heated, what happens? OH is easily eliminated from the system. So almost 600 degrees C almost gone. Okay, crystallization started from here, but as H minus metal hydrogen bond and still survive even after crystallization. Okay, metal hydrogen bond is very, very stable, almost impossible to remove the system because H minus substitutes the oxygen vacancy. This is a constituent of the amorphous structure. That's why the elimination is almost impossible. And the concentration of the OH minus and metal hydrogen bond is almost comparable. So according to our data, so that OH doesn't not so important. So that the H metal hydrogen bond is very, very critical. Okay, so we calculate the optical absorption band of the metal hydrogen bond. Located here, just above as valence band top. Okay. So this is a schematic and illumination illustration of the energy level. Oxygen vacancy is above 1.1 eV, above the valence band top. So the H minus metal hydrogen bond is the bonding orbital. corresponding to this location. Okay, so we think that this is the major origin of the observed and subgap state in oxide semiconductors. Okay, so the how-to demonstrates that this model. So that we fabricated the sample with different base pressure during the deposition, hydrogen concentration. Okay, when the hydrogen back pressure of the hydrogen concentrations increase, this subgap state the intensity is also increased. Okay, so this data shows that the metal hydrogen bond give a subgap state of a valence band top. Okay, so the next is the how to avoid the NVIS. So the most straightforward is to enlarge the band gap. Okay, so that we fabricate and increase the band gap to 3.5. So that the problem is how to reduce valence band top ionization potential. So we selected the gallium. So that when the gallium is increased, so that the band gap is much increased from the 3 eV to the 4 eV. Okay, it's much wider, ultra wide gap as amorphous semiconductors. And as NVIS instability doesn't occur so much. Okay, this is a demonstration. So that when amorphous and exo TFT is exposed to in the sunlight, okay, TFT its offset is not realized. Okay, under such a light. So that but ultra wide gap is TFT. Okay, that even in such a light condition, so that offset is obtained. We didn't participate as active layer. So even such a rough condition, NVIS is much suppressed. Okay, so that from here we focus on amorphous oxide semiconductor to OLED. So that this is the current situation of backplane to drive OLED. Or the amorphous silicon is impossible. LTPS mobility is high, and IGGO is an intermediate. So the problem of the LTPS is not so easy, almost impossible to apply the large-sized backplane. Okay, and very expensive. So but the problem of the TFT, the device structure of the OLED, that is to say, this is currently used OLED, and it's like a galaxy, small size. That is to say, P channel and LTPS is driven. Okay, so that and so drain is connected to the bottom anode. So that when such a P-type TFT is replaced by oxide N-type, so that the source is connected to the bottom. This is pretty bad because the current through the OLED is controlled by the current through OLED. This is fluctuated. So this is pretty bad. So to eliminate this such a instability, we need to connect to the drain connection. That is to say, inverted structure is much better. Okay, so that why the inverted structure is not so easy to fabricate. This is the injection layer material. That is to say, and room level of the organic is very small. Electron affinity is organic is less than 3 eV. Work function of such a material is very large. Okay, so lithium fluoride plus aluminum as the composite electrode is applied. So but this combination doesn't work for the normal inverted structure. That is to say, aluminum first and lithium fluoride is second. In such a sequence, and work function doesn't reduce so much. So that's why normal type is used. So that, we would like to realize that low work function material, chemically stable, intrinsically low work function, and optically transparent. We need to find such a material. And also, as electron as transport layer is also a problem. This is the old one, it's the LQ3, the 10 to the minus 6. So maybe the best material for the organic electron transport layer is the 10 to the minus 3 or 10 to the minus 2. Okay, 10 to the minus 2 is very low for my sense. Okay, oxide is minimum 1. So that we would like to develop the new electron transport layer, electron injection layer, and the electron transport layer. And also the poor chemical stability is very, very problem. So that we need a chemically stable, transparent, and high mobility material. Okay, this is the electron injection layer we developed. This is my favorite material. This is a calcium aluminate doped with electron. Okay, so this is the crystal structure of the C12S7 nanocage structure. So we doped electron like this. Okay, this is almost metal. Okay, work function is 2.4. Electron occupy the interstitial position, not belong to the specific atoms. So that the electron work as an anion. So this is the first room temperature stable electrolyte. Electron work as an anion. Okay, but the work function of this material is 2.4, very, very low. But as fabrication of this thin film, we need a high temperature. That doesn't work practically. So we try to fabricate the amorphous C12S7 by sputtering, so that obtained this one. Okay, amorphous, and work function is 3 or 3.1. This is intrinsic property. And this is sputtering target. This is a photograph of the resulting thin film, completely transparent. Okay, work function is 3. Okay, this is 200 nanometer. Okay, why it's such a low work function and chemically stable and it's optically transparent material realized? So the very, very simple. Okay, so the constituent as cation, the aluminum and calcium. Both of neither of as cation can trap electron. Aluminum 1 plus is unstable. Calcium 1 plus is also very unstable. So that's why the electron occupies and still keep an interstitial position. That's why work function is very, very small. And also, this is optical absorption. So this is 3B. So there no visible absorption and big visible absorption in this region. That's why this material is transparent and chemically stable. Okay, so the next one is the electron transport material. So we developed a new material, zinc silicate. Okay, so this is the work function is 3.5. So the mobility is 1. So the two tells the truth. Mobility is 1 is not so attractive as a oxide semiconductor, but for the application for OLED, so 1 is enough because it's the currently used electron transport layer in OLED is very small, 10 to the minus 2 or minus 3. Okay, this is several order of magnitude higher, and this is completely transparent and chemically stable. And also, quite interesting is that this is X-ray diffraction shows that the diffuse pattern, so that it looks amorphous. So that when this sample is deposited on the rough surface of the ITO, so obtained the top layer becomes smooth. So we don't need to polish the top layer of the ITO. just by depositing sequential deposition of the GSO. Okay, so the exceptionally low work function of the amorphous C12S7 and nu tau means that GSO. Okay, this is the work function of the metal. So the metal potassium is 2.4, and calcium and lithium is almost close to the C12S7 amorphous. But this is chemically unstable, this is chemically stable, and this is not transparent, this is completely transparent. And amorphous GSO is 3.5. Less than the magnesium, so that please compare the work function of zinc oxide. Zinc oxide is 4.5, it's 1 AB less. Okay, that's why this material is very, very exceptional. So that I will show you later why such an exceptional property is obtained. Okay, so one of the interesting feature of the GSO is easy formation of the ohmic contact with various metals. This is ITO, this is aluminum. Okay, so that irrespective of the work function of the cathode was metal, so this material can form ohmic contact. Okay, so this is the energy diagram of the inverted OLED structure, and this is a hole injection. This hole injection is here, electron injection is here. So that ohmic contact is obtained from the cathode metal, and it's GSO, and this layer is a high electron mobility, and C12S7 is a low, very low work function. And so by applying these energy diagram, we can expect it as efficient the inverted OLED. Okay, this is data. This is electron-only devices. Okay, this is the stacking of the devices, inverted, normal, and okay. So this is an IV characteristics of the inverted structure using lithium fluoride and aluminum. Okay, so show this here. So this is a normal stacking of the lithium fluoride and aluminum. This is our inverted structure of the C12S7 and GSO. So that this is the most efficient compared with other one. And quite interesting for me is this is OLED, almost the same. Okay, so our concern is to suppress short circuit. Yeah, okay, because short circuit is very, very serious issues. Because an electron transport layer is very, very not so thick. Because the currently used organic electron transport layer. Its mobility is small and strongly colored, so that it's impossible to thick layers. So that we examined the thickness dependence of electron transport layer, 40 nanometers, 3 to almost 1 order higher thickness. So that you can see almost the same properties was obtained. So that this layer is. We can apply a thick electron transport layer for OLED. Okay, this is a process. We would like to propose a new fabrication process. That is to say, so we learned a lot. So the LCD process has a lot of advantage. Okay, large size glass substrate is absolutely needed. Okay, so Gen 8 is used, but after that, Gen 8.5 factory is started, Gen 8 factory is gone. Yeah, this is the history of the OLED. That's why we'd like to apply the OLED LCD process. That is to say, this is one of the example. So there's a substrate, ITO with the cathode, aluminum, and GSO, the C12S7, from here to here. Sputtering on large size glass substrate. After that, the sample is stable, so that the multi-layer sputtered thin film was taken out from the chamber, and so applied the organic application, and organic process can be applied from here to here. Yeah, so the easy wet etching from here to this 3 layer is very easy simultaneously. Oh, this is a photograph of the C12A7 Gen 6 size of sputtering target. Okay, so that the remaining time, okay, so I'll show that why GSO have exceptional properties. Okay, okay, this is the TM of the amorphous GSO. Okay, so that G is a nanocrystalline zinc oxide. Nanocrystalline zinc oxide is randomly packed. Okay, so that but silicon layer, and since silicon layer is covered by nano-sized zinc silicate. Okay. Okay, this is a quantum size effect of the zinc oxide. Okay, so that from 2 nanometer to 20 nanometer, so the band gap is drastically dropped. Our data follows on this literature, so it's almost the same line. Okay, this means that nano size as zinc oxide quantum dot is the formation of such a nano-sized zinc oxide quantum dot is formed and separated by insulating and zinc silicate layer. The mobility is going down, but still keep a 1. So the work function is 3.5 because that's okay. So that the band gap is much enhanced with decreasing radius of zinc oxide. So that's why the conduction band minimum is pushed up. That's why work function is decreased. Okay, but quite an important thing is this quantum dot, wave function of the quantum dot is spatially isolated by this insulating layer. Okay, that's why electron quantum size effect is observed. But these two zinc oxide nanoparticle is connected electronically by hopping conduction. Okay, the maximum mobility of the hopping conduction is 1, almost 1. That's why this is mobility still keep a 1. So this is optically confined but electrically connected. We use this microstructure to realize such a material. And also carrier is doped in this layer. That's why ohmic contact is easily obtained by tunneling. Okay, so that's I'll show that two examples, two applications of the GSO. That is to say, this is an ITO, 150 nanometer. Okay, no polish. After that, GSO is overlaid deposit, so that the RS the roughness is continuously going down, and also, as current density is such a peaky. This is a sign of short circuit is reduced, so that GSO thick layer is very effective to suppress formation of the pinfall or short circuit. Okay, so the next is example of the application of the GSO to a tandem OLED. So that this is amorphous GSO as used as an electron transport layer, and the whole transport layer is molybdenum oxide, and the work function of these two materials is totally different. But this material can make an ohmic contact. That's why we expect that
voltage drop it's become minimized for tandem OLED structure. This is the result. So that our data shows that a minimum of the 0.4 EB voltage drop is obtained by using this bilayer charge generation layer. Okay, almost time to stop. Okay, so that's if you are interested in oxide semiconductor, these books are maybe very useful. So one is John Wager's the book. This is almost 10 years ago, but this book is very, very well surveyed as literature and history of the oxide TFT, oxide material. And also this is Toby Marks edited. I'm also contributed. This is transparent electronics. And this is Martin's it's a book, and this is David Ginley, and we edited the book, and it's transparent semiconductors. Thank you very much for your attention.
One question is, for interesting, the study on the hydrogen from hydride. Right? Is the hydrogen molecules get to the oxygen vacancy first and then react, or just dissociate the outside, then get to the sides? So they get to the oxygen vacancy first, intact with the hydrogen molecule, H2, right?
Yeah.
So you have measure that intact molecules.
So that in the vacuum chamber, remaining residual gas is always hydrogen or the water. So the hydrogen is everywhere.
But did you measure hydrogen molecule in the oxygen vacancy side?
Yeah.
Okay. Yeah, that's really interesting. Yeah, for the copper oxide, you go to diagonal, go to iodide. Why didn't you go vertically down to like a sulfide or some other?
But sulfide, and sulfide is the copper sulfide is not transparent.
Oh, you want to do TCO?
Yeah, so the iodide is only as transparent material.
Okay, yeah. Yeah, and another question for amorphous, in general, amorphous material, actually, I mean, it's not like crystals, so every atom's in registry, right? So is there any, kind of study on the degrading or aging modes, for example? Guiding principle to make some robust amorphous materials.
Yeah,
right?
that's why. So the amorphous semiconductor TFT. So it's post annealing. Post annealing 300 degrees C is absolutely needed. As the deposited state, so the property is changed with the aging. After deposition, post annealing at 300 degrees C is very important.
You just go back to iodide. You see, it's not transparent, right? For copper iodide, it's not transparent, right?
Yeah, iodide is very.
Yeah, so you go to copper, go to oxide, go to iodide, right? Iodide is also not transparent. So
no. And copper iodide is transparent. Copper iodide is transparent. Yeah. One gap is 3B.
Yeah, thanks for nice talk. There's a lot of talk about replacing indium for ITO and so on. So since there's so many other oxides, what do you think is the good candidate to replace indium?
Indium. So maybe zinc oxide.
Zinc oxide, which is not stable.
No. So other transparent conductors. Transparent conductors. But the TFT is consumption very same. The consumption and the volume is very small.
No, but ITO is used in a lot of other materials too.
Yeah. So but the company doesn't change. Etching is very difficult.
As the price of indium keeps going up, they have to change.
No. So that indium is not so rare. tell the truth. So when so zinc and indium and the copper, these elements simultaneously occurred in the nature. So they're almost the same.
I'd like to ask a question. You say you have this calcium oxide, the composite that has a work function of 3.1 electron volt, and air stable.
Yeah, air stable.
That's rather amazing.
Yeah,
because magnesium, lithium, they all stable.
Why?
Well, I mean, not why. I mean, exactly how stable is stable.
Yeah, okay. Yeah, okay. So
if you leave it out to air, does it get oxidized and the work function goes up and so on?
No, it doesn't change.
Not at all?
No, it doesn't change.
What about heating?
Heating is, so the 200 up to the 200, maybe no problem. But after the 200...
Okay, because OLED is extremely sensitive to any change in the contact. Have you make your OLED device and then check the voltage rise over time to see whether it increases?
Yeah. So we examined the multi-layer as a spot thin film and taken from the vacuum chamber, placed in the outside, and the next day we deposit it on the organic, but the property doesn't change so much.
What about with a real device and then let it age?
Yeah.
Over time.
So what? So
that's a different. You just make your calcium oxide and then you leave it out for a day and then you make the cell out of it and then the device performance is the same, but it's not the same as when you have to see the calcium oxide, the electron injecting layer in the cell and then trying to do the stability test on it.
Yeah, so we didn't do this stability test, but exposed to the ambient atmosphere is not so important. So the nitrogen atmosphere is enough.
So what is the advantage of the oxide transistor over nitride base, gallium nitride base?
Okay. Nitride base is and so large size, and so nitride semiconductor cannot be obtained.
How large you're talking about?
3 meter by 3 meter.
Okay, meter size. Okay.
Display is larger the better.
So transistors are used to drive a huge range of displays, right, in terms of size and also in terms of the technology itself, OLED and LCD. Would it be the situation that there will be one oxide fits all, or would there be different oxides for different display technologies and sizes?
Yeah.
Thank you.
Yeah, maybe the one oxide is much better. So the backplane should be a 1, or any kind of all type of the display.
Would that be IGZO then?
Yeah.
Or would it be, it would be. So end game, that's it, IGZO.
Yeah.
It has been found.
Yeah.
So guys, don't work on it then.
Okay, I have one more question. So this related to OLED.
Yeah.
And also related to the terminologies. And you have developed an electron transport layer.
Yeah.
And you have developed an electron injecting layer.
Yeah.
In one of your diagrams, no, at the end of it.
Yeah. Just
showing the order of the two layers.
Yeah, this one.
No. Keep going.
This one?
Keep going.
Down.
This is the tandem structure.
Oh, yeah.
Okay. I think it's above. Because what I'm trying to say here is that the electron injecting layer, we have the electron transport layer above the electron injecting layer. And then the electron transport layer is always adjacent to the emitting layer. But in your case, the function of your electron transport layer is not the same as the function of our organic transport layer. That's very important. Because in your case, you're developing two electrodes. Okay, one is the ITO, and on top of that is another electrode, we call it electrodes, which is not as conducting as ITO. So you can use that to tailor your optical properties or to reduce the shorting problems with direct contact. But that electron transport layer does not necessarily help the organic LED in terms of the device performance. Because if you put that directly on top of the organic LED, then there may be other things that happen. And also another question is that your electron injecting layer is directly on top, adjacent to the emitting layer. That can produce unnecessary quenching. Yeah. So I mean, those sort of things need to be sorted out in applying the oxide electron transport layer to organic limiting diodes.
Okay, so the electron concentration of the amorphous C12S7 and GSO is carrier concentration at the ferrum level is very low, 10 to the 14 to the 16. No problem.
Maybe it's a no problem. Yeah. And also in this particular case, your ZSO has to be sputtered directly on top of the organic stack. So we talk about this also. That could be a problem as well. But nevertheless, I think this is an exciting field. If we could use an oxide semiconductor to replace everything except the emitting layer, I think that would be quite interesting as an alternative to the conventional organic LED.
Now as even in as aluminum electrode, so some group has developed much as a sputtering mode of the aluminum electrode by sputtering on the organic layer.
Yeah. Sputtering is more manufacturing.
Yes, sputtering. Yes, we need as a LCD process to compete with LCD. This is our policy.
Now we want to overtake LCD.
By the way, we've made gallium nitride TFT using sputtering. Performance not so good.
You did.
My question is, why did Samsung bother to make the wall with a micro LED? Why bother? Why would they bother to do that?
Because they can make it bigger. I mean, bigger than the conventional OLED. It's very difficult to make increasing the size.
So small size is okay, but the large size is not so easy.
Right. So that's essentially replacing everything with gallium nitride based. The micro LED, they're all gallium nitride based.
So even in a transistor, at the backplane, so the gallium nitride, it's a
gallium nitride base, gallium arsenide base, the micro LED.
So that's not homogeneous. So the polycrystal.
You just piece them together with small pieces.
No. The homogeneity is very, very critical for display. So the 3 meter by 3 meter.
Yes, that's true, but they selected to piece them together. They didn't make that one big thing in one time.
So the LTP, so the almost the same situation of the LTPS.
Well, maybe we can talk to Samsung about it. Well, thank you, Professor Hosono, for giving us a wonderful talk.